Alrighty, Mr. Gatekeeper here. We're now on the third video from my hand, boy. The heck was that? Something fell off the table all by itself. Got ghost over here, don't we? Third video here from my my buddy Mr. Astra and whoever else may watch this possibly in the future. We are going to cover the third building block from the first video. Inductors. Although we don't usually use the word inductor much while we're building and repairing these amplifiers, usually you'll hear us usually use a word like choke or coil more than anything. Okay. Inductors are measured in henries, millihenries, microhenries, etc., which you really probably won't be even reading inductance really when you start off. I did not even start reading inductance myself until probably about a year ago, and but once I got into reading inductance, it really did open up a big door for me and shine a light on areas that were dark. And really cool to be able to actually be able to measure inductance, etc. But it definitely isn't something that you have to know to build these things. And a lot of stuff we'll be covering will be stuff you really don't have to know to build them. But I just want to cover, to me, what's in my brain of understanding of this, at least some of the basic things. And, you know, maybe getting into a few things that may be a little bit more advanced too, that may make sense in the future. So, I got transformers listed up here at the top because without a transformer, you have no amplifier. And this is the biggest way that we use inductors. The biggest, most important way we use them in building these amplifiers. Okay. A transformer wouldn't be a transformer without inductance. Okay. So a choke, sorry about that, it got cut off, an alert came up. So anyway, remember when we were talking about with capacitors, how DC electricity cannot flow through a capacitor in series? Well, the cool thing about an inductor or a choke, it can be wrapped in a fashion if it's at the right amount of inductance, which is the measurement of it. Unlike a capacitor, a choke can actually block AC. While a capacitor can block DC, a choke can block AC. And using these two elements together, these two components together, you can pretty much control the flow of RF, which is AC, radio frequency, and DC. You can control the flow of them. Kind of like, for some reason, I don't know why I always think about this, but it's almost like a person in the street controlling the flow of traffic. It just comes to mind. With these two elements, you can do that with these two types of voltages, DC voltage and AC voltage. There's two main chokes that we will be using in these amplifiers. The first one is an air wound choke. The next one is which we'll be using the most of, are ferrite chokes. Here's an example of a ferrite choke. Okay, this right here is a ferrite bead, and since you can see that it's shiny, I should have wrote that down on here, by the way. Actually, I can do that right Type 43 is usually shiny. Type 61 usually is not shiny. I've never seen 61 be shiny. See this bead right here, how it's shiny? Okay, now take a look at this bead. I don't know if you can tell. If you can tell by the video or not. I don't think you really can. Sometimes you'll see some 61 that might have a tad bit of shine to it, but not like this, where you can see it's glossy type. That's a 61 core ferrite bead. This is a 43. They're just made out of different material. Okay. But here's an example of a choke that's wrapped with a 1/2 inch by 1/2 inch 43 core ferrite bead. And since this choke has 3 wraps, it's going to have a certain type of inductance. The amount of wraps wrapped around it controls how high or how low the inductance is. Okay. Here's an example of an air wound choke, which we'll call them coils. As you see, it's just a piece of copper wire that's just had been wrapped around something. That's all it is to it. It's been wrapped around something, and there's 2 wraps. We use these on input and output L circuits for impedance matching. Alright, so what do we use the ferrite chokes for? For different reasons. The main reasons is to block AC, to filter out RF, which really is the same thing that number 1 says. It's just a different, getting more detailed about it. To filter out RF off of a wire or a circuit. To build transformers for our amplifiers. That's the main reason why we'll be using ferrites for. Or to help, ferrites also help to contain an electromagnetic field. So having a lot of ferrites together, as you see, this right here is a choke, right? So it's got a certain type of inductance. Well, this right here has 1, 2, 3, 4, 5, 6 of these ferrite beads, 3 in a row, and has wire wrapped around it. So this has an inductance as well. But it's put in a form like this, the ferrite, to help keep an electromagnetic field stable. Okay. But there's more going on too with this, which I will explain in a minute. And like I said, there's going to be 2 types of ferrite that we use. The first one is type 43. That's the shiny stuff. 43 is good from 2 to 30 megahertz. I wrote 3 down there. 2 to 30. 2 to 30 megahertz. And type 61 core is good from 2 to 50 megahertz. That's just the type of material that this is made out of. These are the 2 types that we'll be using. Alrighty. Now we get into the fun part. Transformers. Which I think I'm going to take a pause for the calls here just in a minute. After we go along a little bit of this, and go eat me some lunch and then come back. But transformers, the meanings in the word transform. There's many types of transformers, but the particular type that we're using are RF transformers. the proper name for these type are called binocular transformers, because they look like binoculars, you know, 2 ports, if you can see, 2 holes. And I need to grab me one that ain't got wraps around it so you can really see the physical makeup of it. Let me see here. Here we go. Alright, see. And these transformers are made with 3 things, and 3 only. And I meant to have all that stuff out too, so I could just lay it down and show you. I may bring it out after I eat lunch. You see the front and the back of the transformer? This actual stuff right here. This is called phenolic board, or copper board. It's the same copper board you see right here. This is copper board. It's just got holes cut. As you can see, holes cut. And that copper board's on there just basically to help with the physical construction of it so it's easier to use. And there are brass tubes. These are brass tubes. Let's see if I can. Actually, I think I got a broken transformer over here which I can actually show. Yeah. Yeah. Good. Here's a broken transformer. The ferrite broke on this one during shipment, and you can actually see that brass tube. See, that's just a brass tube. You can use a brass or a copper. Brass is cheaper. There's really no benefit or either or. So the brass tube goes through both holes, as you can see, and basically they use a thing called my dang brains done went. I've got one in the house. Oh my goodness. They use a die, a special die. It's just like kind of looks like a drill bit. And they press these, like you can imagine that the brass tube's just poking through just a little bit. They press them so that the brass tube bends down onto the phenolic board and basically keeps it stable, like you see here, so that they can have a solder connection. And they make them with, I cannot believe my brain is doing this to me right now. I've got one in the house. That is embarrassing. Their machine, their physical press, arbor press. God, the money. They're called arbor presses, and it's just a press. It's made for putting major pressure through. So, 3 elements: the phenolic board, as you see, the ferrite bead, and a brass tube that holds the beads. Of course, that bead broke, so that's why you can see. So that's how the transformers are physically made. Alright, I'm going to take a pause for the calls, and then I will return and start this back. And as you can see, we got different lengths of transformers. This is a small one. This will be called an input transformer. We use the smallest transformers for our input transformers, meaning that's where the signal is going into on the front end. The smallest signal, which is coming from our radio, is going into the input transformers. And then your larger transformers are going to be your output, your longer. Transformers come in many sizes, lengths, etc. These are the main size that I've used for years, which is a 1/2 inch by 1/2 inch bead. You will see other builders, they use a bead called a 5/8 core bead. But this is the size that I use. I learned from a very smart man that, of course, it's cheaper. And also you have no issues at all making the same amount of power with these than the other ones. So this is why I've always used these style 1/2 inch by 1/2 inch beads. So I'm going to take a pause for the calls, go eat, and I will come back and we'll finish this video up. I'm going to go into how these transformers are used and what they actually do, which I didn't learn until way after I was into building these things. I had been building these things for a good minute before I actually learned what they were actually doing. And once it's explained and you have just a little bit of knowledge, it's very, very easy to understand what's actually going on. And always remember, a transformer is called a transformer because it's transforming something. Something to something. That's the definition of transform, for something to change from one state to another. Alright, I'll be back. Alrighty, let's get back to it. Alright, and like I said, a transformer is used to transform one impedance to another. I know we haven't covered impedance or anything like that yet, just kind of put that to the side. Impedance is something I don't even understand nowhere near the way I should. But dealing with this, here's just one thing that you need to remember. Dealing with these type amplifiers, we are always trying to get the input and the output of the amplifier as close to a 50 ohm impedance. All the antennas, all the radios, etc., they're all run on 50 ohms. So just remember that 50 ohms, 50 ohm impedance. Okay, well, the way the transformer works is once you match the impedance that you're trying to match to, something happens which is called resonance, and that means you're going to have a maximum power transfer. Okay, I'll explain that with a transistor. Here in just a second. And as you can see, this is a little bit different of a transistor than you saw in the other video. This is still a 2879, just made by a different company. Okay. So we're dealing with input and output transformers. Looking at this amplifier right here that I'm working on. Here's the input transformers. This is a 4-pill amplifier. 1, 2, 3, 4. Here's your input transformers, output. The wire that we use in our transformers is called Teflon. The actual jacket is Teflon. I can take a torch right now and put it on this wire and it will not melt. This wire is designed to not chafe as easy when you're wrapping around the transformer, and it's also designed to withstand high amounts of heat and not melt. That's the wire that we pretty much use majority in the whole amplifier, at least I do. About the only wire I don't use in the amplifier that's not Teflon. Teflon is the power and ground wire, the DC wires. Okay. A transformer consists of 2 windings. Now here's where we're going to get into a cool part that I didn't even understand the first 3-4 years I was doing what I was doing. I just never had anybody explain it to me this way. But once it did, it just unlocked a whole big shebang, a big gold nugget of understanding. A transformer is not a transformer without at least 2 windings, 2 or more windings, because we're dealing with RF here. Okay, we're dealing with alternating current. Once resonance is made, the RF signal travels from one winding to the next through an electromagnetic field called a flux field. I didn't write that down, but And this is not a physical happening. This is not done physically. So your signal is going into the amplifier through this little coax cable right here, into the amplifier, actually travels from the first winding in this transformer to the next winding, which is touching the transistor's leads electromagnetically through a flux field. Alright. There's a broken transformer, but here's a transformer. Alright. You notice how on one side there's a split. You see it? And the other side there isn't. So it looks like this type of formation. Excuse me for a second. So it looks like this type of formation. Okay. But we're going to write it this way for now. Alright. So that, what I just wrote right there, represents your actual first winding. Your low Z winding. Just think low because it's one wrap for now, okay? Your low Z winding. This is your first wrap. This is a physical wrap. So it's kind of unique that the brass tube and the phenolic board, see this split right here down the middle, but on this side, and it is not split, it's shorted. It's kind of unique that, I didn't mention it before, this is used to hold the transformer together and to make it easier to use, solder into place. But it's also used as the first winding, as the first wrap. So this is actually your first wrap. So when you wrap this transformer with wire, that's your second wrap. So there's your first wrap, right? Your first wrap, you can look at it like this. Your first wrap is the transformer itself, in a sense. Not the ferrite beads, just the transformer, the phenolic, the brass tube, phenolic, brass tube, phenolic, a U. That's one wrap. That's considered one wrap in the RF world. Now when you sit here and wrap wire around it, this would become your second wrap. And that could be, it would be your high. Your high Z side. Alright. So here's how it works. An RF signal is introduced to this side of the transformer. And if you take a look at the transformers right here, they're soldered down to these little strips, okay? And in the middle of these little strips, there's a gash, just like you see the gash here. So they're separated. All right, and then the transistor itself solders to these strips. So the transistor is actually connected on the input transformers and the output transformers. They are connected on the low Z part of the transformer, which is actually part of the transformer itself. Okay, so the RF signal comes into the transformer itself. Let's say, for example, we got a big transistor right here. This is just as an example, okay? Just as an example. The signal that's coming into the transformer is a 50 ohm signal. Remember, like I said, we run on 50 ohms with what we do. 50 ohm antenna. This thing down right here is a 50 ohm dummy load. I cannot key my radio without it being hooked up to this dummy load right here or an antenna, or I will fry it. It's got to have a 50 ohm load. Okay, so the radio signal is 50 ohms, and but here's the issue here. Okay, this transistor itself does not run on 50 ohms. We're only going to use this number as an example. Let's say that this transistor, the input of this transistor, let's say, this is just an example, okay? This ain't actually real, but let's just say as an example, it needs a 10 ohm signal, a 10 ohm impedance before it will accept full power, before full power can actually go into the transistor to be amplified. Well, that's what this transformer is here to do. To transform this 50 ohm signal, this is just an example like I was saying, to a 10 ohm signal. So the 50 ohm signal comes in this portion of the transformer, and the RF signal travels through a flux field, which is an electromagnetic field, to the high Z part of the transformer, which is your wraps. I've got this backwards. I do have this backwards. This is the way that we would look at it on the output side, actually. I've got this backwards, but I'm just going to leave it be because I've got the orientation of the actual transformer right here backwards. But we're just going to leave it here for an example. I'm not really caring about trying to be correct about that. Actually, we're using this as an example. The signal travels to an electromagnetic field to the next. Like with this example, this would be called the primary side of the transformer. This could be called the secondary, okay? Whichever one where you're putting the signal in and coming out, etc. So then the signal is sitting on the secondary side. And now the transformer has transformed the 50 ohms to 10, and it's going to the transistor. This is just an example of how the transformer actually works. Now, check this out. Like I said, this transformer is designed like this to make it easier on us to use them. So we can solder them to strips like this, etc. Make it easier for us to solder capacitors, as you see right here, on top of the transformers. That's why there we go again. Let's see if I can't recover from this. I figured out somehow last time how to get rid of it. When I start zooming in and out, sometimes this will happen. I'm just going to press stop and come right back. Alright. Now let me show you this. Alright. There's absolutely no difference from this transformer. This is an input transformer. And this. Alright. As you see, these are two ferrite beads. And I have two sets of wire wrapped into the ferrite beads. The white wire is wrapped around them one time. So the white wire comes in and out. So that would be your low Z. The red wire is wrapped 3 times. See? 3 wraps and comes out. So it would be orientated just like this in the picture. So the red would be the high Z. I could actually take this right here. I could make 2 of these right now. and take these and solder them in a circuit just like this. Of course, I'd make the wires shorter and everything, but I could take these right now, solder them in a circuit just like this right here, where it's split right here, right here. Take the other one, solder it there. Then your signal would actually come in on this side of the transformers. Okay, but if we were using these on the output, it would be flipped around like this. So the signal coming from the output of the transistors would go into the white wire, your low Z end, and then the high Z end right here would be carrying the signal on out the amp. There's a little piece right here that I haven't covered yet, which I wasn't planning on covering in this video, but I may just go ahead and do it real quick. Which is another reason why we use ferrite beads. Now take a look at this. This right here, I think, by the way, I think I covered the transformers pretty good. I think I covered that pretty good. I was just letting you see the transistor. Just as an example, I'll put that back over there. So I think I did the transformers, covered that pretty good. I think I explained that pretty well. An electromagnetic field. The signal travels from the first winding to the next winding. One winding, one winding. The transformer itself, phenolic brass tube, is one winding, which is always going to be one wrap. The next winding is the wire that you wrap around it. Alright, this right here can be a splitter or a combiner, and take a look at it. All it is pretty much two pieces of wire that are connected together right here. Alrighty, phone died that time. So here's another use. I'm sorry if this looks blurry because I ain't got my brightness turned up real high, and it's been kind of looking blurry. But anyway, so if you see, this is a ferrite bead. There's two wires. Each of the wires are wrapped around the bead twice. See, 1, 2. 1, 2. Two of the wires connect together right here and solder together. And here is the other end of the other two wires. This can be used as a splitter or a combiner. This is how we combine two pill sections together to make a 4-pill. As you can see, it's just I ain't a very good artist, you know. It's wrapped around it twice, wrapped around it twice. So this is a splitter or a combiner. Sending the RF signal this way and splitting it into two signals. That's how you use it as a splitter. And you reverse it around and use it as a combiner, taking two signals in this way and combining it to one. Let's see if I can't get this amplifier right here. Turn it around this way. This is an older build that I've done a few years ago, quite a few years ago. If you see, here's one right here, ferrite bead. See the coax right here, which is coming from the relay. The signal comes in this direction, goes to this ferrite bead, splits off to this transformer, splits off to this transformer. So the 50 ohm signal is being split off both ways. Then the transformers, they do what they do. and transform the signal. These two transformers at this point is called a impedance matching network, along with the capacitors on top of them. They transform that 50 ohm impedance and go down lower in ohms to what the transistors need. Then the signal goes to the transistors, and then the transistors amplify the RF signal. Then these transformers right here pick that signal back up to distribute it, to transform it from low now up back to higher, which is 50 ohms. And then, see, these are two pills. That's a 2-pill section. That's a 2-pill section. Now this device is acting as a combiner now instead of a splitter. So now it takes this transformer's wire and this transformer's wire and combines them. If you notice, the other wire of these transformers are soldered to the board to ground. Same with this. As you see, one wire of the transformers to ground. One wire right here is to ground. The other wire goes to this splitter of each transformer. If you take a look at these are chokes, which I showed you earlier. Right here. So it's a choke. Those are chokes. I used to put them on transformers and that way right there. Now I do them a little different. I solder them with less wire. But so there you go. I think that's a pretty good lesson, really. I want to show you one more portion. Take a look at these big things right here. Now that's a big choke. Excuse me. On the other amplifiers, you may see people just taking a simple choke like this and soldering it from here to the back of the transformer like that, which is perfectly fine too. This is just a way that I do it. I hadn't done none this big in a while, but these chokes right here are here for two reasons. If you notice this blue wire, that's the power wire. Power wire comes in and solders to this long piece of copper board right here. This is a piece of copper board that's glued down to this board to keep it separate. And this is where the DC power comes into, solders to that board. So these two chokes, as you can see, they're soldered to this board too. So they are sending the DC power. This is two wires. The DC power goes through these two wires, wraps around this bead. One wires go to this part of this pill strip. These are called pill strips, which you solder two leads of the pill, the input and output of the pill to. And this wire comes down to that side. This right here is feeding the DC power, the DC electricity, 12, 13, 14 volts or whatever, to the transistors. That's the first thing that these are doing, okay? The second thing that these are doing is, like I said, this is now where DC and AC connect. The transistors, see, we're using this pretty much on 27 to 28 megahertz. That's RF AC voltage at 27 megahertz, 27 megacycles, 27,000 rotations a minute. You can kind of look at it up and down 27,000 times a second. So this wire is bringing in the DC electricity, okay? Well, it's soldering to the pill strip where the pills are connected to, and the pills are sending the amplified AC signal, which is RF, that's going into this transformer. So AC is present on these wires now. And we don't want that signal coming back down, back this direction down your power wires, through your power wire back to wherever the power wire is coming from. We want to keep that AC signal off this power wire as best as we possibly can. Keep it as low as possible. Or it could cause interference. It could cause damage to other places. If you're at the house, hell, that RF could flow through your wires in your house or whatever. So that's what these chokes are for, remember? Chokes can block AC. So these chokes are here to minimize that RF, to keep the RF off the hot bus as much as possible. That's what these chokes are for. Whether if it's a choke like this or like this, that's what they're there to do. Of course, since these have more wraps and it's a bigger ferrite, this is going to keep more of the RF off the DC line than this with just 3 wraps. But it don't matter which way you choose to do it, that's what it's doing. So that's what that's there for, to feed the RF, to feed the DC, the power, the 12 volt, 13, 8, 14, 15, whatever volts you're running at, to the pills, to the transistors, and to also keep the RF, the AC, off the DC line going back. And I think that's enough for one lesson. I covered a good bit coming to this. And that's pretty much all that we'll be using these for. And if you take a look right here, see how I got a little bead right here on the power wire? See? That's all it's there for. Is that right there is just part of the network. That bead gives me a small, just a little bit more chance of trying to keep some RF off the power wire. That bead doesn't do a whole lot because it's just one bead on the power wire and it's not wrapped around, but this is where it's doing most of the job of keeping the RF off. But by habit, everybody usually puts a bead or two on their power wire. And putting that bead on the power wire just gives it a little bit more inductance on the power wire in the helping of trying to keep the RF off that power wire, because you do not want that RF, because the RF that comes out of these amps can cause some crazy interference, dude. I've got some funny videos uploaded that some of my best performing videos of me showing what this RF can do coming out of these things, man. They can go through intercoms, open and shut doors, go through computer speakers, go through open and shut bank doors, send the little canisters in the bank back to the woman. If you got enough RF, you can even change the red lights. I mean, but you don't really want to do that type of stuff. You want to have an amplifier that's clean as possible and set up. Because if I didn't have this choke on here and all that, and I just had the power wire coming in, or let's say I had these transformers, the back of the transformers soldered directly to the hot bus, if I had the hot bus pushed in closer and then soldered to the butt right here, and then that soldered, the power wire soldered in, I would have a heck of a lesser chance of keeping the RF. It's just a safety procedure, that's all it is. It's not something you actually have to have for the amp to work. It's just a safety feature. And these chokes right here, I won't get into what they're doing right off hand, but these right here are part of the bias of the transistors, which we will not get into right now. We'll get into that later on. But this right here is what you call a Class C amplifier. There's a lot to learn, my man. Just a little bit at a time. So I don't quite know what we will be getting into next, but I have had this bag of tricks that I've been carrying with me. And one thing I see that we hadn't got into yet are relays and switches, which I'm pretty excited to get into. The switches are very easy to understand once they're explained. I mean, everybody knows what a switch is, because everybody pretty much on this earth, or at least in the Western world, has used a switch at some point of time. And as you can see, man, these transistors, they create a lot of heat. That's why they're mounted to this big heat sink up under here. And that's why we got a fan blowing air down in there, goes through the heat sink, comes out the back, to attempt to keep that thing cold. Alright, I'm done. I'm going to go ahead and compile all these videos together. My homeboy, Mr. Astra the Master. One more step closer to getting you on these things, my man. I'm building these bad boys, these big mauls that people enjoy dropping the hammers. They call them mauls, they call them hammers, they call them boxes, they call them linears, they call them amplifiers. Lots of names for these little devices here. But when it comes down to it, they're just electronic devices made to amplify an RF signal that's already present. And I'm good and gone after that. 73rds. Bye, bye, bye. Like that portfolio piece.